Homework 3.4, the rational zero theorem, zeros of polynomial functions, video 2. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. Again, nothing here yet, but wait until the next video. All right, so let's take a look at another example of a function that I've already got. Not only do I already have it up here, but I've already got it factored for you, and I've got the 3 zeros for the function. And remember, what we're attempting to do in this video, as well as the previous, is look for hints in the original function that tell us what these zeros might possibly be. Obviously, the difference in this one and the previous one is that 2 of our zeros are fractions. So we're going to have to keep track of where all of those numbers went. So we're going to keep track of where they went the same way we did in the previous video. We're going to take each zero and turn it into a factor and then slowly remultiply it and keep track of all the pieces. So let's do the same thing we did before. If you have zeros and they actually have factors. Now here's where we got to use a little bit of, I don't want to say hand waving or smoke and mirrors, but according to the factor theorem, if x equals 1/2 is a zero, then x minus 1/2 is a factor. And although there's nothing wrong with that factor, it involves something that's not an integer. And when we multiply it all out, our answer will. So there's really more than one factor for any given zero. For example, if you had x equals 2, that could have come from this factor, x minus 2, but it also could have come from this one. Think about it. If you solve this equal to 0, you get 2. Or it could have come from this one, 10x minus 20. So for any given zero, there's actually an infinite number of factors because you can take this and multiply it by any number you want. If I multiply it by 3, I get this. If I multiply it by 10, I get this. So in an effort to keep things nice and integer, when our zeros are rational numbers but not integers, we can set up a factor according to the factor theorem, x minus this value. But in order to not have a rational number here, to not have a fraction here, why don't we multiply this by a constant that will eliminate the fractions? So for example, if I multiply this by 2, this would become a 2x and that would become a 1, you know, just like this. So as we're building our factors from rational numbers, try to build them so that they don't contain rational numbers, but rather integers. And again, all you have to do is x minus this and then multiply the thing by its denominator. And the same thing here. If we did x minus -5/3, which would be x plus 5/3, that has a fraction. When I multiply it all out, I'll get a fraction, but my function doesn't have a fraction. So let's use a multiple of this factor that has no fractions. If I triple all of this, it would cancel the 3 into the 5, and the x would pick up a 3. This one's a little bit easier. It's x minus -4, so x plus 4. Okay, so let's slowly start multiplying, but at the same time, let's keep track of all the numbers that determined the zeros. For example, this 4 determined this 0, and this 5 helped to determine this 0, specifically its numerator, and this 1 helped determine this 0's numerator. But what about the denominators? I think it's pretty transparent that this 0's denominator came from this leading coefficient, and this 0's denominator came from this leading coefficient. And even though this isn't a fraction, you could think of it as over 1, and its denominator came from the leading coefficient. So let's keep track of where all these numbers go. And remember, when we multiply these things out, we're both multiplying terms and adding like terms. When you add things, there's an infinite number of ways to make that happen. For example, if I said, give me 2 integers that add to give 6, there's an unlimited pair. 1 and 5, 3 and 3, 2 and 4, -2 and 8, -3 and 9, and it could go on forever. But if I said, give me a pair of integers that multiply to give 6, I'm very limited. 1 and 6, 2 and 3, -1, -6, -2, -3, and that's it. So as we're keeping track of these numbers when we multiply, we really want to focus on the terms where that's all we do is multiply. Anytime we combine things to make like terms, we're going to lose track of the original values. So it's only the products that we need to focus on. All right, so speaking of products, let's start to multiply this out and keep track of things. Let's start with the first two. When I FOIL this, the first thing I do is 2x times 3x. That's just a product, so we're going to keep track of that result. 6x squared, we'll double underline that in green to keep track of it. Now, when we do the outside and the inside, they are products, but they're also like terms, so they're going to get added, and we'll lose track of the numbers that got added. So we'll do it, but I'm not going to underline it. The outside is positive 10x, the inside is negative 3x. Positive 10x and negative 3x is positive 7x. And then the last part of FOIL is just a multiplication problem, so we'll keep up with it. -1 times positive 5 is -5, and that 5 we're going to keep track of. We haven't done anything over here yet, but I am going to write the 1 because I did the same thing with all the other leading coefficients. Excuse me. And then if we finish multiplying it out, again, I only want to keep track of 2 of the numbers when they get multiplied, and that's it. If I do any combining of like terms, I'm adding things and I lose track of that number. So, and I'm going to do this a little more efficiently. Here's how I multiply these things. Let me find my x cubes. This product is the only one that will make an x cubed. 6x squared times 1x is 6x cubed. There was no addition there, so we're going to keep track of that product. Let's find the x squareds. And when I say find the x squareds, I mean, how can I multiply something from the first factor times something from the second factor to get an x squared term? 6x squared times 4 is an x squared term, but so is 7x times 1x. So those are going to get combined. Not going to keep track of them, but I'll write it down. 6x squared times positive 4 is positive 24x squared. 7x times 1x is positive 7x squared. 24 and 7 is something. Something is not going right here. Sorry, but as you can expect, I had things already figured out previous. So, I found the problem. I found the problem. You may have seen it also. Wait, did I find the problem? No, everything that's actually written up here is okay, but that's all right. I accidentally miswrote something when I did it over here. In fact, yeah, there's a problem here, and if you're paying attention, you might have seen it, and we're going to have to do some damage control. Remember when I told you that this factored into this? According to my work on the sideboard, it is the correct factorization. But I made a mistake going from here to here. Do you see it? If x minus 4 is a factor, and I'm looking for zeros and put that equal to 0, what do you get when you solve that? Not -4, but +4. The move from here to here was correct, but the move from here to here was not. This should have been a +4. This should have been a minus. This should have been a minus. And luckily, since I'd worked this out in advance, I knew I was about to get something that didn't match that. But, whew, dodged that bullet. Where was I? Oh yeah, x squareds. Now, it's -24x squared and +7x squared, which is -17x squared. Don't care about that number because it was part of adding, and you can't unadd and get a finite pair of integers. Let's find the x terms. Let's see, one way to make an x term is positive 7x times -4. That's -28. And here's another product with an x term. -5 times 1x, that's -5x. So -28x and -5x is -33x. But because that was obtained by doing some adding, I can't recover how it was created. And then the constant term can only come from one place, the product of these constant terms. It is only a product, so we'll keep track of it. -5 times -4 is +20. Double underline that in red. So what does this all mean? Well, first off, notice that we got back the original function. Despite the fact that I made an error, at least I caught it in time before it was a catastrophe. Our whole objective here, and this is going to be summarized in the next video, is if you give me a function, and my goal is to find its zeros, I'm going to use synthetic division. But in order to do that, I need to put a number in the box. If you don't give me a number to put in the box, where do I look? Well, the good box numbers are our zeros. So where did the pieces of the zeros land up down here? Well, the 1, the 5, and the 4 were all essentially numerators, and together they made the 20. The 2, the 3, and the 1, the denominators, the 2, the 3, and the 1 were the denominators, and together they made the first number. So we're about to blow the lid off of this, but the hints for what might be possible rational zeros, possible meaning they may or may not be, rational meaning they could be fractions, but that includes integers, and zeros meaning a value that makes the function equal to 0. The hints about the possible rational zeros are contained exclusively in the leading coefficient, whose factors may be denominators, and the constant term, whose factors may be numerators. Let's formalize this in the next video.